All right, it's May 4th. I'm going to be going, hopefully you're safe and healthy. I'm going to be going through the through lab exam 2 practice. Please remember, lab exam covers experiments 6 through 11, so no 12, right? There are pieces of 7 we cut out, so when we get to it, I'll say not that one. But I sent you the copy of the exam with the ones crossed out. Also note experiment 6, you want to go back to lab exam 1 to find the practice, okay? So for experiment 6, we had it in lab exam 1. All right, we have on the first page and half of the second page, I want to say, questions where we just have to circle a choice. So you have to find the correct choice. So the first one is problem 1. Which of the following pure compounds exhibits hydrogen bonding? So it's a question about hydrogen bonding. So number 1 is about H bonds. And H bonds require an HF, HO, or HN bond, right? So you're looking for a molecule that has that. So your only molecule there that has that is HF. So the correct answer is HF. Second question, the energy of a photon of light that is 13.2 nanometers equals how much energy in joules, all right? Unique E equals H nu. This is energy, that's frequency, and then you need nu lambda equals C. So if you look at this, you have energy equals H. You move that over or move this over and you have C over lambda. H was given as in a side paper, 6.63 times 10 to the minus 34 joules second. C is 3.00 times 10 to the 8 meters per second. Those are constants, so they would be given with the problem. And then you have to divide by the wavelength, but it has to be in meters. So I have 13.2 nanometers, and there are 10 to the 9 nanometers in 1 meter. Okay? So, got a calculator here. We have 6.63 exponent 34 negative times 3 exponent 8 divided by 13.2. And if this is 1 over, then it's multiplied times 1 exponent 9. And I end up with 1.51 times 10 to the minus 17. 1.51 times 10 to the minus 17 joules. So that's the answer for the second one. Third one is number of valence electrons in H3O plus. So I go oxygen, oxygen gets 6 dots. I have to leave 3 free for the hydrogen to dock. But since oxygen gets 6 and that's gone, then I give him 5. 1, 2, 3, 4, 5. And then that's where the hydrogen comes in. And then the whole thing has a positive charge, right? And if I have to do his geometry, he is pyramidal because he has 4 pairs, of which 3 are used for bonding. And if I have to do his polarity, because of that, he's ionic. The number of valence electrons is 8, right? 8 valence electrons. Next one, molecular geometry of SF2. So SF2, so sulfur in the center. sulfur's atomic or number in the periodic table. Do I have a periodic table? Because I'm gonna need one soon. Ah, I got one right here, good. So he's on Roman numeral 6. So he gets 6, of which 2 have to be left free for the fluorine to dock. So there's a fluorine. And there's a fluorine, right? So I have, this is a set of 4, of which 2 are non-bonding and 2 are bonding. So this is bent. He also, by the way, happens to be polar. TeCl4. So TeCl4. Te is under family 6 also. But chlorine's looking for 1, so I better leave 4 of them open. So there's 4, 5, 6. And a 0 here for chlorine, and I give him his other 6 electrons after I put down. The first one, it's not an issue to make chlorine smaller than tellurium because chlorine is way up here, right? He's a 3p5, where tellurium is a 5p4. So as such, he's going to expect it to be a bigger atom anyway. So I'm looking at this. This is a set of 5 with 1, 2, 3, 4 bonding, 1 non-bonding. So steric number 5. This is a C-salt. So he looks something like this. If I have to draw him in 2 dimensions, right? And so he's definitely polar. That was not part of the question, but we're just adding it in so that you can practice. H3O plus, notice I asked you that one again. We have it here, it's pyramidal, right? Which of the following is non-polar? So we already know that TeCl4 is polar. We already know that SF2 is polar. We're left with ASF3, ASF3. So AS atomic number 5, of which 3 have to be left free. 1, 2, 3, 4, 5. 0F, 0F, 0F. This guy's pyramidal, right? He's uneven. So he looks like this. Again, having to draw him in 2 dimensions, but he looks like a pyramid, trigonal-based pyramid, trigonal pyramidal. And then BeCl2, BeCl2. Be gets 2, 1, 2, Cl, Cl. So he's linear, non-polar. Right, this guy was polar and trigonal pyramidal, or just pyramidal. That's fine if you just want pyramidal. So it's BeCl2 of the 4 that is non-polar. Which of the molecules is polar? That one's actually easy because we already said SF2 was polar. So since we said SF2 was polar, now you put him in a list with some other ones. You can pick that he's the one that's not polar. Okay, product of the reaction between Mg and O2. So metals as well as non-metals plus O2 make oxides, right? So Mg, he's in Roman numeral family number 2, right? So you know your ions, he's an Mg plus 2. Oxides are a minus 2, so it makes MgO, right? Because Mg is a plus 2 and O is a minus 2. Product between SO2 and H2O. So SO2 plus H2O. This is a non-metal oxide. Non-metal oxides make acids, so H2SO3. Notice that we're keeping the same oxidation state. This is a +4 oxidation state there, and this is a +4 oxidation state. That's why this does not make H2SO4. Name uses for elements or compounds in LEDs. That's not a valid question. We didn't do that. That would be experiment 8B. When placing stearic acid on oil, so this is oil, so this is hydrophobic. And stearic acid has a polar head and a non-polar body. This is hydrophilic. This is hydrophobic. Like attract like, so, whoops, do that. This is how we might line up on an oil surface. So the tails of the molecules would be attracted to the oil. That's the part that would be the non-polar tail, would be attracted to the non-polar oil. Okay? And that's why water and oil don't mix. Water is polar, oil is non-polar. In the experiment in which you collected data to find R, you used the silver wire instead of copper wire to wrap your magnesium. What would that have caused your R value to look like? Well, we wrapped the magnesium in copper because we use the magnesium, right? So in that experiment, the Mg determined how much H2 gas was produced, right? So if we had wrapped the Mg in a wire that reacts with with acid, then there would have been also hydrogen produced from the reaction of that metal with acid, because many, but not all, but many metals react with acid. You know this from experiment 5 when you did the activity series. However, CuHG do not react with acid. So then there would be no effect in R if you substitute Ag with copper. Now, if you substitute it with aluminum or zinc, or any of the metals that do react with acid, then your experiment would have generated an R that was off. Okay? So I combined volumes A, liquid A plus liquid B, and let's say 25 ml plus 25 ml, and the mixture is 52 ml. I'm just giving numbers here, right? So I combined liquids A and B, and the volume was larger than the sum of the pure volumes. So that tells me that A and B don't want to be next to each other. So A and B are upset with each other, okay? And so they spread out a little bit, and that's why the volume's a little bigger. So they have to fight, they have to expend energy to get away from each other, so the container will get cold. Right? Because they're taking energy from the surroundings, and the container is part of the surroundings, to try to get away from each other, to repel each other a little bit. This is opposite to what happened in experiment 11. When you combined ethanol and water, the volume was less. You took 25 and 25, and it was more like 45 ml or something like that. And the solution got hot. The solution got hot because water and ethanol love each other. In getting close to each other, they went to a lower energy state and they released energy. so that the solution as a whole gets hot because energy is being released. These guys are fighting each other. That requires energy, so they're trying to take energy from the surroundings so the container will get cold. And then the interaction with them, between them, is repulsive. Okay, they hate each other for some reason. Okay, so they maybe both don't hydrogen bond, or don't both, you know, have different properties. Maybe mix the polar with a non-polar. Hess's law is part of experiment 12, so that's not a possible question. Which of the following forms an acid when placed in water? So oxides, metal oxides plus water make bases. Non-metal oxides plus water make acids. So you're looking for who here starts with a non-metal, and you have sodium, magnesium, aluminum, and phosphorus. So it's P4O10. Okay, and we're done with the first side. Second side. This, which of the following is expected to have the largest energy band gap? That's experiment 8B. We did not cover it, so we're not going into it. Mercury height difference. So a height, whoops, that's not a height, that's a density. A height in Hg is 45.0 cm, right? And a height in material X is 145 cm, right? So I've got my units right. What is the density of liquid X? So it's density of mercury, height in mercury equals density, that's not the symbol for density, density in liquid X, height in X, right? So I have 13.6 is the density in mercury. The height, they're both in the same units, so I'm good. 45.0 equals X, I should call it X. This is the density of X, 145. Density of X equals 13.6 times 45 divided by 145 is 4.22. 4.22 grams per ml, because the density of mercury here is in grams per ml. Realize that as long as your units for height are the same, then you can use them. You could have used centimeters, you could have used inches, you could have used whatever, as long as they're both the same. All right, next problem. Yeah, that one's not fair because we didn't cover it. We didn't cover the green solution, but let me show you this a little bit so that you know. You know the colors of the primary colors are red, yellow, and blue, right? So they form a triangle, right? And the secondary colors are for these two purple, for these two orange, and for these two green. And they sort of form another triangle, right? So when you see a solution that's red, the color it's absorbing from the spectrum is green, right? So you have a red solution here. You're sending white light through it, right? When you see over here is that you're going to see that the green is what's gone, right? Because the solution looks the color of what it doesn't absorb, right? So it's absorbing in this range. And so for that question, if you have a green solution, then it's absorbing red. It's the complementary color is the main thing it absorbs. But we didn't cover that in experiment 7. because we were in a hurry to get experiment 7 done. So as to get into the world of online experiments, a lot of experiment 7 is a visual thing, playing with light, so it was sort of difficult to turn it into an experiment easily, so we decided that that's a place we needed to cut back a little bit on. Okay, but that experiment had Beer's law, right? So Beer's law was the one about absorbance, so you had each plotted concentration as a function there, absorbance here, you have to have units for concentration, and the thing was linear, right? And you're able to find concentrations once you measure their absorbance, once you have what they call, this is a Beer's plot. So you need to be able to remember that because that was an important part of experiment 7. The other part of experiment 7 that was important, we'll be covering in a question soon, but it's about the hydrogen spectrum. So that's the one thing we did in experiment 7, the hydrogen spectrum, so that we understood that quantum mechanics is valid, right? That the experimental data we collect from the hydrogen lab matches results and predicts, even transitions in electronic states. The second thing is we wanted you to learn about Beer's plot. So I think it's Beer-Lambert, but everybody calls it Beer's, all right? So expect something on it in some way, right? What do solar cells do? They convert visible light into electric current, but please note that was part of experiment 8B. We did not do that. Which will correspond in the emission of light of the shortest wavelength. So energy for light is proportional to frequency, right? That's why E equals h nu, right? So if this goes up, that goes up. However, when you look at frequency, frequency is C over lambda, those two are inversely proportional. So this one is 1 over wavelength. Oops, didn't stay over wavelength, right? All right, so when this increases, that decreases, okay? So this question says you're looking for the shortest wavelength, shortest lambda. If he's small, then that makes this big because they're inversely related. If that's big, it makes this big. Means largest, oops, sorry, I'm in a room with a sensor. Energy, right? And then the second thing that matters here, it's emission. Emission means it's going from high end to low end, okay? So a lot of this, I find it's easier to just remember the hydrogen spectrum. If you remember, the equation follows a number over n squared, right? So that was Bohr's equation. So you have your n equals 1. Then you had your n equals 2, some separation, but then now it was smaller. You don't have to get it exactly right. You just have to realize that each time it's smaller. Okay? Going up is absorption. Of energy, so you need energy to pop it up to a higher energy level, and going down is emission, right? So you're looking for the one that has the greatest difference, because this was an energy diagram, right? So 3 to 4 is an absorption, so it's not good. 4 to 3 would be this. Right? Okay, that's one of them. 3 to 5 is going up, so it's not an emission. 5 to 3 is that one. Okay? 4 to 5 is going up, so that's not an emission. 5 to 4 is that one, right? So you're being asked which of those arrows going down is biggest. So it is 5 to 3. So n equals 5 to n equals 3 is the one with the shortest wavelength. Right? Again, I find it easier to just do the drawing. Also remember that you could calculate that energy. If you want the energy for that transition, it would be 2.18 times 10 to the minus 18 joules. And then it would be 1 over 3 squared minus 1 over 5 squared. Realize that if you flip them, it doesn't matter, it just changes the sign. Whether you're going up or down determines the sign, and remember that, you're learning that now from thermochemistry. But the sign is irrelevant if you're looking for the energy difference. The diagram will remind you if down is emission and up is absorption. Okay, you have two gases, helium and oxygen in a flask, Hg and O2. Just to remind myself, this one's 4 grams per mole, and this one's 32 grams per mole. Okay? They're in separate flasks. They have the same pressure and volume. They contain the same mass of gas. Which flask has the highest temperature? Okay, we have PV equals nRT. Okay? So separate flasks, they have the same pressure, so that's not it. And they have the same volume, so that's not it. And R is a constant, so that's not it, right? So if I put this all together, I have a constant equals NT, right? Because all these guys are constants, so they're the same for both sides. And so then it's asking me, I have the same mass in both flasks. So let's say I have 4 grams of each, 4 grams of each. So I have 1 mole of this guy and much less than 1 mole of this guy, right? So whoever has the highest moles has to have the lowest temperature to keep this constant. So the question is asking me, which flask has the highest temperature? Well, if I want the highest temperature, I need the least moles. So O2 is the flask with the highest temperature, okay? Another way to do this is just make your life easy if you want. You can make this 1 atmosphere, and you can make this 1 liter, and you can even make this 1 if you want. And then you can plug in the numbers, because in the end, whatever 2 you multiply, so you made this 1, 1, and 1, this number is a constant 1, you can use the actual numbers to decide a fate temperature and decide which of the 2 values is bigger. So one way is to reason it out mathematically, like I just did. I put all the constants on one side. The other way to reason it is to actually just give the numbers that are saying a number and make it an easy number. 1 atmosphere, 1 liter, I even made the constant 1. Who cares? He's a constant, right? Because I'm just trying to find the relationship, not the exact answer, okay? All right, problem 2. And again, as I erase and all that, you can move this up, speed it up. You don't have to sit here watching me erase. And you can backtrack and you can slow down to take an image. So question 2 is not valid. That's experiment 12. It's Hess's law. Okay, question 3. I mean, if you wanted, you could, I don't know if you've covered it in lecture yet or not. So you could use it as a practice problem for your test or whatever. And then 3 says you're given 67 grams of UO2 and excess HF. So that's trying to tell you HF is not the limiting reagent. And they want you to figure out what volume of gas you make. Okay? So you have UO2 plus HF there's 4 of him, goes to UF4 plus 2H2O gas, right? And so you have a solid and a liquid, a solid and a liquid, making a solid and a gas, so he's the only gas being made. There's no mention of collecting it over water, so I don't have to worry about the vapor pressure of water, but if it was there, I'd have to think about it, right? There's no mention of a height difference in the column in a burette, so I don't have to worry about correcting for it. So I'm straight with a PV equals nRT problem. PV equals nRT problem, okay? So the guy they want is volume, right? So I go volume equals nRT, and I'm gonna move this over actually. Volume equals nRT divided by P. Okay, so I have to find N, right? So I have to find N. I have 67.0 grams of UO2, 1 mole of UO2 equals, I gotta find uranium in my periodic table. Uranium is 238, and then oxygen 16, so 238 plus 16 plus 16. Weighs 270 grams per 1 mole. And he's good to 3SF, right? It's just that he ends up being a 0 at the end, but he's good to 3SFs. And then I can use that there's 2 mole of H2O for every 1 of UO2. So that gets me N. So I have 67 divided by 270 times 2. I got 0.496 mole of H2O. He's got infinite number of sig figs, 3 and 3, so this guy's good for 3 sig figs. 0.496 mole. Okay, you can keep one more digit if you want. All right, R is a constant, 0.08206 meter atmosphere Kelvin mole. We give you the constant. Temperature was 245. We got 245 plus 273, so I can have it in K, because it has to be in Kelvin. Then I divide by pressure. Pressure 766 m of Hg. But for this to work out, it has to be an atmosphere. So I go 1 mole is 760. That's not the right unit. 1 ATM is 760.0 m of Hg. So I have everything in the correct units. Mole and mole. Mercury, mercury, atmosphere, atmosphere, Kelvin, Kelvin. So I'm left with liters as my answer. So liters, 0.496 times 0.08206 times 245 plus 273 divided by 766 times 760. I have 20.9 liters, 3 sig figs, 3, I got him to 4. He's gonna be 3, I got him to 4. So 20.9 liters is what you would get. All right, that's the end of the test. So you have the answers in your seminar section, so you're able to go look at the answers. As I just wanted to quickly discuss it in case you needed some reminders. Oh, so let's do that just to help you out here. So remember, I'll give you constants and I'll give you a periodic table. So really quickly, experiment 6. Right, experiment 6 is stoichiometry. we just did some stoichiometry here with UO2, so you know how to do that. Concentration, right? So concentration had molarity, so molarity is moles over volume equals molarity, right? And then you also have dilution. There was dilution in experiment 10, I think. I want to say, I show you how I diluted the concentrated HCl, if memory serves me right. But this one also has dilution problems, so M1B1 equals M2B2. So that's sort of what comes out from there. Experiment 7. Experiment 7 had, it depends on how you want to use it. I find it's easier to just draw it out, 2.18 times 10 to the minus 18 joules over n squared. There's a minus there in theory, but this is the energy level for those guys, right? So for the hydrogen atom, H atom, right? Or you can do, you know, 1 over n squared minus 1 over n squared to figure it out, the difference, right? To do the delta E. Then you have that E equals H nu, and you have that nu lambda equals C. Where H and C and that 2.8, which is Rydberg's constant, are values we would give you as constants. Experiment 8 had no equations. Experiment 9, so experiment 8 is about patterns of reactivity. Right? Experiment 9 is about Lewis dots. Then figuring out steric acid and all that, or steric number and all that, so you could get geometries and polarity, right? And then experiment 10, that was where you had PV equals nRT, and you had density of mercury, height in mercury, equals density of water, height in water. So that allowed you to calculate the height of mercury associated with a certain height of water. And the height of mercury is the pressure. And then you also have to worry about correcting for the vapor pressure of water. And then experiment 11 has quite a few calculations in it, but all of them are dimensional analysis. None of them are a new equation. It's actually all you're doing is using all the dimensional analysis you have learned, okay? So, for example, you find, for example, the mass of steric acid. In monolayer. And you want the volume of the steric acid. Well, guess what? Mass is equal to, or mass can be changed to volume by using a density, right? So you have, the density would be ml up here and grams here. So this is 1 over the density, right? So it's all about dimensional analysis. It seems like it's equations that are hard for you, but it isn't. It's just dimensional analysis. You have 50 drops, let's say, equals 1 ml. Then you're trying to find the volume of a drop. Then volume of 1 drop would be 1 ml divided by the 50 drops, right? So that would be 0.020 ml per drop. Okay, you have to change it to angstroms. 1 meter is 10 to the 10 angstroms. So it's all about some sort of dimensional analysis. And nothing about that calculation is really that difficult. You found the area, right? Area of the circle. Then that equaled the area of your monolayer. And so now you have to find the height of your monolayer. So volume equals area times height, right? Again, equations you have used in high school. So none of experiment 11 is really that overwhelming in calculations. It might seem that way to you, but it's all about straightforward dimensional analysis. So think about that if there is a problem on doing calculations for experiment 11 in the test, okay? All right, I'll leave it there. I get to now do the same thing for the lab exam for Chem 1B.